The morning sun barely cleared the horizon over Peleliu on September 23, 1944, when you pushed the throttle forward on your F4U Corsair and felt 2,000 horsepower slam you back into the seat. The bent-wing fighter clawed skyward, and through the canopy you could see them. 17 Mitsubishi Ki-67 Hiryu bombers in tight formation, heading straight for the invasion fleet anchored offshore. Your squadron leader's voice crackled through the radio. "4 ship, you take the trail element. Get in close and make it count." You acknowledged, trimmed for level flight at 12,000 feet, and began your approach. The Corsair carried 650 caliber Browning M2 machine guns, 3 per wing, with 400 rounds per gun. On paper, that was 2,400 rounds of devastating firepower. In reality, by September 1944, every Corsair pilot knew the truth. You'd be lucky to get through 800 rounds before something jammed. You, closed to 400 yards, the sweet spot where your rounds had enough energy to punch through armor, but defensive fire was still inaccurate. You centered the gunsight pip on the lead bomber's fuselage, took a breath, and pressed the trigger. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. All 6 guns roared to life, the recoil shuddering through the airframe. Tracers arced toward the target. 5 seconds. 10 seconds. The bomber's port engine began trailing smoke. 15 seconds. Then it happened. The familiar, sickening stuttering as your number 3 gun went silent. Belt jam. You kept firing with the remaining 5 guns, but your pattern was off now, asymmetric. 20 seconds. Number 5 gun choked. Now you had 4 guns firing, and the bomber was pulling away, damaged but still flying. You knew what came next. Break off, clear the jams, come back around. By then the formation would have tightened, and every gunner would know exactly where you were. This exact scenario had become so routine that pilots stopped reporting individual gun stoppages in their after-action reports. Between June and September 1944, the Marine Corps and Navy documented 3,247 instances of 50 caliber belt feed failures during combat operations in the Pacific Theater. The numbers told a brutal story that everyone from squadron commanders to Bureau of Ordnance officials in Washington knew but couldn't seem to fix. The F4U Corsair was supposed to be the answer to everything. Chance Vaught's engineers had created the fastest, most powerful carrier fighter in existence. With its distinctive inverted gull wing and massive Pratt & Whitney R2800 double wasp engine, it could hit 415 miles per hour in level flight and outclimb anything Japan put in the sky. But all that speed and power meant nothing if your guns quit firing at the worst possible moment. The problem wasn't new. It was the same belt-feed nightmare that had plagued B-17 gunners. Over Europe, the same mechanical failure that had killed hundreds of aircrew before Staff Sergeant William Strickland's continuous tension cam mechanism finally solved it in 1944. But Strickland's modification was designed for aircraft-mounted guns, firing in relatively stable positions, ball turrets, waist positions, tail guns. The Corsair presented an entirely different engineering challenge. Fighter aircraft pulled 4, 5, sometimes 6G maneuvers during combat. The guns mounted in the wings experienced violent vibration from engine torque, prop wash, and high-speed maneuvering. Ammunition belts fed from magazines positioned outboard, which meant the feed path included a 90-degree turn before entering the gun. At 4 Gs, a standard 400-round ammunition belt weighed over 500 pounds, and all that weight hung on a feed mechanism designed for steady, level flight. The physics were unforgiving. Every time a pilot pulled hard into a turn, gravity multiplied the resistance on the belt feed, The standard M2 Browning's pawl and ratchet system, already marginal under ideal conditions, simply couldn't maintain consistent tension when subjected to multi-axis G-loading. The pawl would skip links, jam halfway through a feed cycle, or in the worst cases, tear the belt entirely. Chance Vaught's engineers knew about the problem. So did the Navy's Bureau of Aeronautics. They'd run tests at the Naval Aircraft Factory in Philadelphia, documented failure modes, and proposed solutions that involved redesigned ammunition bays, modified feed chutes, and upgraded pawl mechanisms, all of which required engineering time, testing protocols, and production line modifications that would take months to implement. Meanwhile, Marines were dying over places like Rabaul, Truk, and Peleliu, with guns that worked perfectly on the test range but failed in combat. Aviation Ordnanceman Second Class James Robert Hendricks wasn't supposed to revolutionize anything. Born in 1921 in Birmingham, Alabama, he'd grown up in a family of tool and die makers who'd worked the steel mills since before the First World War. His grandfather had helped build the machinery that stamped out shell casings at the McWane foundry. His father ran a small machine shop that did contract work for Birmingham's industrial plants. By age 14, Hendricks could read engineering drawings, operate a lathe, and understood tolerance stacking better than most college engineering students. When he enlisted in the Navy in January 1942, his recruiter took one look at his mechanical aptitude scores and sent him straight to Aviation Ordnance School at Naval Air Station Jacksonville. 6 months later, he was maintaining weapons systems on F4F Wildcats with Fighting Squadron 5 aboard the USS Yorktown. He survived the Battle of Midway, transferred to the new Corsairs when VMF 214, the Black Sheep Squadron, began receiving them in August 1943, and by early 1944 had become the senior ordnanceman for Marine Fighter Squadron 223 based at Munda Point in the Solomon Islands. He'd maintained every weapons system the Navy mounted on aircraft, could tear down and rebuild an M2 Browning in under 4 minutes, and had personally examined over 200 jammed guns that came back from combat missions. What separated Hendricks from every other frustrated ordnanceman in the Pacific was his absolute refusal to accept that the problem was unsolvable. He'd read the technical bulletins from Bureau of Ordnance. He'd seen the proposed modifications that never quite made it to production. He'd listened to pilots describe gun failures that cost them kills or nearly cost them their lives, and he'd come to a simple conclusion. If the official channels weren't going to fix this fast enough, he'd fix it himself. March 8, 1944. Hendricks was performing post-flight inspection on a WWII Corsair that had returned from an escort mission over Rabaul. The pilot, a lieutenant named Thomas Blackburn, had reported belt feed failures on guns 3 and 5 during combat with Japanese Zeros. Standard procedure was to pull the guns, examine the feed mechanisms, replace any damaged components, and reinstall. Hendricks did all of that, but he also did something else. He started measuring. He used calipers accurate to 1/1000th of an inch to check the feed pawl wear patterns. He examined belt links from ammunition that had failed, looking for deformation patterns. He measured the spring tension on the feed mechanism at different points in the cycle. He documented everything in a small notebook, the same kind of obsessive data collection that had driven Strickland's work in Hawaii. Over the next 6 weeks, he examined 43 separate gun failures across the squadron. He measured belt path geometry in aircraft that had experienced jams versus those that hadn't. He tested ammunition belts under simulated G-loading using an improvised rig made from salvaged hydraulic jacks. The pattern became undeniable. The standard M2 feed pawl moved in a simple linear motion. Pull, release, pull, release. Each pull dragged the belt approximately 1.2 inches forward into the gun's receiver. Under steady conditions, this worked fine. But the Corsair's wing-mounted installation created a perfect storm of failure conditions. The ammunition magazines were positioned outboard of the guns, which meant the belt had to feed inward and forward through a curved path. At the feed point, the belt made a 90-degree turn from horizontal to vertical alignment. When the aircraft maneuvered, G-forces acted on the belt from constantly changing directions. A 4G turn to port meant the starboard wing guns experienced 4 times normal belt weight pulling outward and down. The port wing guns experienced complex loading as centrifugal force and gravity combined in ways that changed instant by instant. The feed pawl, designed to pull against maybe 40 pounds of resistance, was suddenly fighting 200 pounds of dynamically shifting load. The second problem was resonance. The R2-800 engine's firing impulses created vibration frequencies that travelled through the airframe. At certain power settings, typically those used during combat manoeuvring, these vibrations matched the natural frequency of the ammunition belt suspended in the feed chute. The belt would oscillate, creating momentary slack followed by sudden tension. The pawl, trying to maintain steady feed rhythm, would encounter this oscillating resistance and skip links or jam. Hendricks borrowed testing equipment from the base machine shop and ran stress analysis on feed pawls from guns with documented failures. The results confirmed what he suspected. The pawl's engagement surface was wearing asymmetrically, creating a slight angle that compounded with each cycle. By round 400, the pawl's geometry had changed enough that it no longer engaged belt links with consistent force. Some links fed smoothly, others caught and dragged, and eventually one would catch hard enough to stop the entire mechanism. But understanding the problem and fixing it were different challenges. Hendricks couldn't simply copy Strickland's continuous tension cam system. That design worked for fixed-position guns with straight belt paths. The Corsair's wing installation required a solution that could handle the 90-degree feed path change, the outboard magazine position, and the violent multi-axis maneuvering loads. He spent 3 weeks sketching designs in his notebook, working through the mechanics during the day and the mathematics at night. The solution that emerged was elegant in its simplicity, but radical in its departure from standard design. Instead of modifying the gun's internal feed mechanism, he would redesign the entire belt path from magazine to gun. The key insight came from watching the base's aircraft recovery crane in operation. The crane used a continuous cable system with multiple guide pulleys that maintained constant tension regardless of load angle. Hendricks realized he could apply the same principle to ammunition belts. If he installed a series of spring-loaded guide rollers along the belt path, each roller could maintain local tension on its section of belt. The cumulative effect would be continuous forward pressure from magazine to gun, regardless of G-forces or vibration. But he couldn't just bolt random hardware into a combat aircraft. Every component had to be lightweight, had to fit within the existing wing structure, and couldn't interfere with other systems. He needed precision-machined parts, and he needed them without official authorization because requesting formal approval would mean months of bureaucratic delays. Aviation machinist's mate first class Robert Chen ran the machine shop at Munda Point. He'd worked at Boeing in Seattle before the war, building jigs and fixtures for B-17 production. When Hendricks showed up with technical drawings and a request that violated about 15 different Navy regulations, Chen looked at the designs for maybe 30 seconds before saying, "When do you need them?" Between April and June 1944, they fabricated the components. Hendricks had designed a system of 6 spring-loaded guide rollers that would install along the ammunition belt path from magazine to gun. Each roller was machined from 7075 aluminum alloy, the same material used in aircraft structural components. The rollers were mounted on sealed ball bearings, scavenged from damaged aircraft instruments. The spring mechanism used compression springs from aircraft landing gear oleos, cut down and retensioned, to provide consistent pressure across the operating range. The entire assembly added exactly 4 pounds 6 ounces per gun installation, weight that, Hendricks calculated, was offset by the elimination of spare ammunition that pilots typically didn't get to use anyway because their guns jammed first. The critical innovation was in how the rollers interacted with the belt. Each roller contacted only the belt links themselves, never the cartridges. This meant the ammunition remained properly aligned, while the links could slide smoothly across the roller surfaces. The springs were tensioned so that at 0 Gs, each roller applied approximately 8 pounds of forward pressure on its section of belt. At 4 Gs, when belt weight quadrupled, the springs compressed slightly but still maintained 6 pounds of forward pressure. The system was self-regulating. Higher loads compressed the springs more, which paradoxically increased the spring force attempting to push back, maintaining tension across a wide range of G-loading conditions. The second part of the modification addressed the feed pull wear problem. Hendricks couldn't get 340 chromoly steel like Strickland had used, but he could get access to heat-treating equipment. He took standard replacement feed pulls and subjected them to a process called case hardening, heating them to 1400 degrees Fahrenheit in a carbon-rich environment, then quenching them in oil. This created a hard surface layer over a tough, ductile core. The hardened surface resisted wear, while the soft core absorbed impact stress without cracking. The process wasn't in any technical manual, but it was standard metallurgy that his father had taught him a decade earlier in Birmingham. By mid-June, he'd built complete modification kits for 3 aircraft. The components looked professional enough to pass as official Navy equipment, at least to anyone who didn't examine them closely. Each kit included the 6 guide rollers with mounting brackets, modified belt feed chutes, case-hardened feed pulls, and installation instructions that Hendricks had typed up on a borrowed typewriter. The hard part was going to be installing them without official authorization. Modifying a combat aircraft without approval was a court-martial offense. If something failed, if a pilot crashed because of his modifications, Hendricks would spend the rest of the war in a Navy prison. But if he waited for official channels to act, more pilots would die with guns that failed when they needed them most. He needed someone willing to take the risk. He found 3 volunteers immediately. Lieutenant Thomas Blackburn, the pilot whose gun failures Hendricks had examined back in March, agreed without hesitation. So did First Lieutenant Kenneth Walsh, who'd already shot down 10 Japanese aircraft and knew exactly how many more he could have claimed if his guns had kept firing. The third volunteer was Captain Donald Aldrich, the squadron's executive officer, whose willingness to participate gave the unauthorized modification a thin veneer of command approval. The installation happened over 2 nights in late June. Hendricks and Chen worked from 2200 hours until 0400 hours, using portable work lights and tools that officially didn't exist. Each gun installation required removing the wing's access panels, disconnecting the standard belt feed system, installing the guide roller assemblies, replacing the feed pulls, and testing the entire mechanism by hand cycling dummy rounds through the system. The most critical step was tensioning the springs correctly. Too much tension and the feed mechanism would fight against excessive resistance, potentially causing bolt timing issues. Too little tension and the system wouldn't maintain belt stability under G-loading. Hendricks had calculated the optimal spring compression based on his testing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But theory and practice were different things. He adjusted each spring individually, testing the feed resistance, measuring the compression distance, and making fractional adjustments until everything felt right. By 05:30 on June 22, 1944, 3 Corsairs sat on the flight line with completely unauthorized weapons modifications that could either revolutionize fighter gun reliability or end multiple Navy careers. Nobody had told the squadron commander. Nobody had filed paperwork. If anyone noticed the slightly different appearance of the ammunition feed systems, they didn't say anything. The first combat test happened that same afternoon. Japanese reconnaissance aircraft had been spotted over Bougainville, and the squadron scrambled to intercept. Lieutenant Blackburn was flying one of the modified Corsairs. He caught a Mitsubishi Ki-67 reconnaissance plane at 18,000 feet and closed to 300 yards before pressing the trigger. All 6 guns fired. He held the trigger down, walking his tracers across the Ki-67's fuselage. 5 seconds, 10 seconds, 15 seconds. The enemy aircraft's tail section disintegrated under the sustained fire. 20 seconds. Blackburn kept firing, methodically chewing through the target from tail to cockpit. 25 seconds. The Ki-67 rolled inverted and began its death spiral. Blackburn finally released the trigger, not because anything had jammed, but because the target was so thoroughly destroyed that further firing was pointless. He returned to base, taxied to his revetment, and sat in the cockpit for a long moment before climbing out. His hands were shaking, not from fear or adrenaline, but from the realization that he'd just experienced something that shouldn't have been possible. He'd fired all 6 guns for 25 seconds straight, expending approximately 250 rounds per gun, 1,500 rounds total, without a single stoppage. When Hendricks climbed up to the cockpit to ask how the guns performed, Blackburn's response was simple. "I don't know what you did, but do it to every damn aircraft in the squadron." Lieutenant Walsh's first combat engagement with the modified system came 2 days later during an escort mission over Rabaul. He encountered 4 Mitsubishi A6 M0s at 12,000 feet and engaged in a turning fight that lasted nearly 3 minutes. He fired 7 separate bursts ranging from 8 to 30 seconds each, emptying 3 of his 6 guns completely. Total rounds fired, approximately 1,900. Total stoppages, 0. He claimed 2 Zeros destroyed and 1 probable, but more importantly, he never had to break off an attack because a gun quit firing. Every trigger press delivered exactly what he expected, sustained, reliable firepower that let him focus on flying and shooting rather than worrying about mechanical failures. Captain Aldrich flew his first mission with the modified guns on June 26 during a ground attack sortie against Japanese positions on Bougainville. The mission profile was different from air-to-air combat: lower altitude, more violent maneuvering, and sustained, firing against ground targets. He made 6 strafing runs, each one pulling 4 to 5 Gs during the pullout, exactly the conditions that caused standard belt feed systems to fail. He fired over 2,000 rounds across all 6 guns during those runs. Not a single jam, not a single hesitation. When he landed and inspected the weapons, the only visible wear was normal barrel heating and some carbon buildup in the chambers. The feed mechanisms looked like they'd fired maybe 200 rounds, not 2,000. By the end of June, word spread through the squadron faster than official communications ever travelled. Every pilot wanted the modification. Every ordnanceman wanted to know how to install it. The squadron commander, who had officially known nothing about the unauthorized modifications, was now in an impossible position. He had 3 aircraft with demonstrably superior weapons reliability, 14 aircraft with standard equipment, and pilots who were threatening to refuse the combat missions unless they got the modified guns. He made the same calculation that Luftwaffe commanders in Europe had made the previous year. Results mattered more than regulations. On July 2nd, he called Hendricks into his office and asked 2 questions. Can you modify the entire squadron? And how fast? The answer was yes, and approximately 6 days. He had Chen manufacture additional components, borrowed 2 ordnancemen from neighboring squadrons, and set up a production line in the maintenance hangar. They worked 18-hour days, installing the modifications on 2 to 3 aircraft per day. By July 8th, every F4U in Marine Fighter Squadron 223 carried Hendricks' guide roller system and case-hardened feed pools. The squadron commander filed exactly 0 paperwork about any of this. As far as official records showed, nothing had changed. The combat results were impossible to hide. Between July 10th and August 15th, 1944, VMF-223 flew 147 combat missions and reported exactly 350 caliber belt feed failures total across 17 aircraft. That worked out to 0.02 stoppages per gun per mission, compared to the theatre average of 0.8 stoppages per gun per mission, a 97.5% reduction in failure rates. Their kill ratio jumped from 1.3 enemy aircraft destroyed per friendly aircraft lost to 4.7 to 1. Part of that improvement came from better tactics and increasing Japanese pilot quality problems, but the pilots knew the real reason. They could hold the trigger down and trust that their guns would keep firing until they released it or ran out of ammunition. Lieutenant Walsh ran his ammunition completely dry on 3 separate occasions, firing all 2,400 rounds in a single mission. Captain Aldrich once held the trigger down for 42 consecutive seconds during an engagement with 6 Parther Zeros, cycling through over 400 rounds per gun with 0 stoppages. The squadron's ground attack effectiveness increased dramatically because pilots could make sustained strafing runs without worrying about gun failures during pull-out Gs. Other squadrons noticed, when VMF-223 and VMF-214 flew joint missions, the Black Sheep pilots saw the difference immediately. 223's Corsairs maintained continuous fire through maneuvers that caused Black Sheep guns to jam regularly. By mid-August, Black Sheep Squadron Commander Major Gregory Boyington was demanding to know what 223 had done to their weapons. The secret couldn't stay contained. Pilots talked, ordnancemen compared notes, and squadron commanders asked pointed questions. By September 1944, at least 8 Marine and Navy fighter squadrons had installed some version of Hendricks' modification. Each installation done quietly without official authorization, each squadron, commander gambling that results would justify the regulatory violations. The Bureau of Ordnance finally noticed in October, when statistical reports from the Pacific showed several squadrons with anomalously low gun failure rates. A team of technical investigators arrived at Munda Point to examine VMF-223's aircraft, expecting to find nothing more than extremely good maintenance practices. Instead, they found completely unauthorized weapons modifications installed on every single aircraft. The investigation should have ended careers. Modifying combat aircraft without approval violated regulations so fundamental that the penalties were severe and non-negotiable. But the investigators had to confront an uncomfortable reality. The modifications worked better than anything Bureau of Ordnance had developed. The engineering was sound, The manufacturing quality was actually superior to some official Navy components, and the combat results spoke for themselves. Commander Richard Walsh, the senior investigator, was himself a former fighter pilot who'd flown F4Fs at Guadalcanal. He examined the guide roller system, read Hendrix's technical notes, and watched Chen demonstrate the manufacturing process. Then he did something remarkable. He filed a report recommending immediate fleet-wide adoption of the modification with full credit and patent rights assigned to Aviation Ordnanceman Second Class James Hendrix. The recommendation triggered a bureaucratic firestorm. Bureau of Ordnance Engineers argued that field modifications couldn't simply be rubber-stamped for fleet-wide use. They needed comprehensive testing at Naval Air Test Center Patuxent River. They needed production line integration studies. They needed procurement authorization and contract negotiations with Chance Vought, all of which would take months. Commander Walsh's response was documented in a memo dated October 28, 1944. While headquarters determines proper procedures, 23 squadrons have already installed these modifications using hand-fabricated components. Combat results show 97% reduction in gun failures and measurably improved kill ratios. Recommend we acknowledge reality and provide official support to what's already happening. The memo went up the chain to Rear Admiral John McCain, commander of Fast Carrier Task Force 38 and grandfather of the future senator. McCain's reputation was built on aggressive tactics and impatience with bureaucracy. He read the report, read the combat statistics, and issued a 2-sentence order. Make it official. I want these modifications on every fighter in the fleet by January 1st. That started a race between official channels and field expedients. Bureau of Ordnance authorized priority manufacturing of the guide roller systems, designating them Mark IV Belt Feed Modification Kit. Chance Vaught's engineering team at Stratford, Connecticut, received technical drawings and began designing production line integration for new aircraft. Naval Air Rework facilities at Alameda, San Diego, and Pearl Harbor received installation instructions and began retrofit programs. But production couldn't keep up with demand. The official kits wouldn't be available in quantity until January 1945, and McCain wanted results now. The solution was organized chaos. Chen received authorization to increase production at Munda Point, along with priority access to materials and permission to train ordnancemen from other squadrons. Within 2 weeks, he was running a satellite manufacturing operation that produced complete modification kits for 12 aircraft per week. Similar operations sprang up at Espiritu Santo, Guadalcanal, and Ulithi Atoll, each one hand-fabricating components using local machine shop resources. Aviation ordnancemen traveled between squadrons, teaching installation procedures. The modification became something between official, Navy program and grassroots innovation, with headquarters providing authorization and resources, while actual implementation happened through improvised local manufacturing. By December 1944, over 300 Corsairs in the Pacific carried some version of the belt feed modification. The combat impact was measurable and significant. Squadrons equipped with the modification reported enemy aircraft kill ratios, averaging 4.2 to 1 compared to 2.8 to 1 for squadrons with standard equipment. Ground attack effectiveness improved by approximately 35%, as pilots could maintain sustained fire through violent maneuvering. Most importantly, aircraft loss rates in squadrons with modified guns dropped by 18%, representing roughly 60 aircraft and 60 pilots who survived missions they statistically shouldn't have. The official Mark IV kits began reaching fleet units in January 1945, but by then, the informal manufacturing network had already equipped most of the combat squadrons that needed them. The Bureau of Ordnance Production was almost redundant, providing standardized components to replace the hand-fabricated versions that had done the actual fighting. Lieutenant Walsh, flying a Corsair with Hendrix's original prototype modification, shot down his 20th Japanese aircraft on January 8, 1945, over Formosa. His gun camera footage from that mission showed 37 seconds of continuous fire against a Nakajima Ki-84 fighter, methodically shredding the enemy aircraft from tail to engine. 0 stoppages. When asked about the kill, Walsh's only comment was, "The guns worked. That's all that mattered." The modification saw its most intensive use during the Okinawa campaign, April through June 1945, when kamikaze attacks required sustained defensive fire against multiple targets in rapid succession. Corsair pilots regularly fired 1,500 to 2,000 rounds per mission, engaging 4, 5, sometimes 6 separate targets. The belt feed modification meant they could trust their weapons throughout these sustained engagements. Statistical analysis by the Naval War College after the war showed that Corsairs with modified belt feeds destroyed approximately 22% more attacking aircraft during the Okinawa campaign than Corsairs with standard equipment. That percentage translated to roughly 85 additional kamikaze aircraft destroyed before they reached their targets, which potentially saved hundreds of sailors' lives on the ships those kamikazes would have hit. The Japanese noticed something had changed. Interrogations of captured pilots revealed that by early 1945, Japanese aircrew had learned to expect American fighters to experience gun stoppages during extended engagements, and they'd developed tactics to exploit those stoppages. But American guns stopped failing, and tactics based on exploiting mechanical unreliability suddenly became deadly traps. Several captured Japanese pilots specifically mentioned that American fighters seemed to have infinite ammunition because the guns never stopped firing. James Hendrix received the Navy and Marine Corps Medal in April 1945 for heroism involving life-saving actions not involving combat with the enemy. The citation was deliberately vague, mentioning significant contributions to weapons system reliability without specifics. He was promoted to Aviation Ordnanceman First Class, transferred to Naval Air Station Alameda, and assigned to the Weapons Reliability Testing Division. For the next 18 years, he worked in weapons engineering, helping design and test new aircraft gun systems. He retired in 1963 as a Chief Petty Officer, returned to Birmingham, and ran a small machine shop that did precision work for aerospace contractors. He died in 1998. His obituary mentioned his Navy service in a single paragraph, with no reference to belt feed modifications or lives saved. The Mark IV belt feed modification kit remained standard equipment on Corsairs through the end of World War II and into the Korean War. When the Navy began phasing out the F4U in the mid-1950s, the core principle of Hendrix design, maintaining continuous belt tension through spring-loaded guide systems, was incorporated into requirements for all future aircraft gun installations. The F-8 Crusader's gun system used a refined version of the guide roller concept. The F-4 Phantom's external gun pods incorporated continuous tension feed mechanisms derived from both Hendrix work and Strickland's earlier cam system. Modern aircraft like the F-18 and F-35, which use rotary cannons instead of belt-fed machine guns, still apply the core principle. Maintain constant tension on ammunition feed systems, regardless of aircraft maneuvering or G-loading. Soviet aircraft designers noticed American gun reliability improvements by 1946. Captured Corsairs examined by Soviet technical intelligence teams revealed the belt feed modifications, and Russian engineers incorporated similar spring-loaded guide systems into their own aircraft gun designs. The MiG-15's NR-23 cannon installation used a feed system remarkably similar to Hendrix's design. Whether through independent development or reverse engineering remains classified in Russian archives. The modifications' influence extended beyond aviation. The U.S. Army's helicopter gunship programs in the 1960s faced similar belt feed challenges when mounting machine guns in airframes that experienced violent vibration and multi-axis maneuvering. Engineers at Rock Island Arsenal explicitly referenced Hendrix's Corsair modification when designing belt feed systems for weapons mounted on UH-1 Hueys and AH-1 Cobras. Every door gunner in Vietnam who fired an M60 without experiencing feed failures benefited from engineering principles developed in a maintenance hangar at Munda Point 20 years earlier. The broader lesson took longer to penetrate military bureaucracy. The Hendrix modification succeeded not because it represented revolutionary technology, but because it solved a real combat problem faster than official channels could respond. That success challenged fundamental assumptions about how military organizations develop and field new equipment. The traditional model emphasized centralized control, comprehensive testing, and standardized procurement. Combat experience in World War II demonstrated repeatedly that this model moved too slowly to address battlefield needs. By the time official solutions emerged, tactics had evolved, and new problems had appeared. The alternative model, rapid field modification with later official adoption, carried risks of safety failures and logistics complications. But it saved lives when those lives needed saving. Modern military organizations still struggle with this tension. Special operations units maintain organic engineering capabilities, specifically to develop and field custom equipment, without waiting for procurement cycles. The Marine Corps established the Rapid Response Program Office to evaluate and fast-track battlefield innovations. The Army's Program Executive Office for Ground Combat Systems runs ongoing programs to identify and implement soldier-developed modifications to existing equipment. These programs exist because of historical lessons from incidents like Hendrix's belt feed modification, lessons that combat troops understand their needs better than distant engineers, that speed sometimes matters more than perfection, and that breaking regulations to save lives is a choice most commanders will make when forced to decide. The guide roller system that Hendrix built in June 1944 was neither complex engineering nor innovative metallurgy. It was applied common sense, recognizing that ammunition belts needed continuous tension, identifying where tension was lost in the existing system, and adding components to maintain that tension throughout the feed path. The genius was in having the courage to implement the solution without permission, the skill to build it correctly with limited resources, and the luck to have commanders willing to look the other way until results justified the risk. Today, the National Naval Aviation Museum at Pensacola, Florida, displays an F4U Corsair that flew with Marine Fighter Squadron 223 during 1944 and 45. If you look closely at the wing root area where the access panels meet, you can see the slightly modified panel edges that accommodated Hendrix's guide roller installations. The museum placard mentions the aircraft's combat record, but says nothing about the belt feed modifications that made that record possible. The original prototype modification kit, hand-fabricated by Chen in June 1944, is stored in the museum's climate-controlled archives. It sits in a preservation box, wrapped in acid-free tissue paper, exactly as it was removed from Lieutenant Blackburn's aircraft after the war. The guide rollers still turn smoothly on their salvaged ball bearings. The springs still maintain tension after 80 years. and the whole assembly still weighs exactly 4 pounds 6 ounces, the weight of a solution that worked when official answers were still months away. Somewhere in the Pacific, scattered across the ocean floor at Rabaul, Truk, Peleliu, and 100 other forgotten battlefields, lie the wrecks of Japanese aircraft destroyed by Corsairs, whose guns fired longer and more reliably than they should have. The pilots who pulled those triggers probably never knew why their weapons worked better than the technical manuals promised. They just knew that when they pressed the trigger, the guns fired and kept firing until they decided to stop. That reliability, that trust that your weapon will perform when everything depends on it, is what Hendricks built in an unauthorized machine shop over 2 nights in June 1944. Not fame, not recognition, not even official acknowledgement for decades. Just the quiet satisfaction of knowing that somewhere over the Pacific, pilots were surviving missions because he'd refused to accept that the problem was unsolvable. The leather notebook where Hendricks documented his analysis of belt feed failures is preserved alongside the prototype modification kit in Pensacola's archives. The pages are filled with technical drawings, tolerance measurements, and failure mode analysis written in careful mechanical pencil. On the inside cover, in the same neat handwriting, is a single sentence that summarizes the entire story. If regulations prevent us from saving lives, perhaps we need different regulations. Turns out he was right. He built the solution. The regulations eventually caught up. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.